All right, here's our third lesson. It's going to be on modeling. And what modeling is when we try to apply math to the real world, and it helps us describe situations around us. It's called applied math, is where this comes up, and it's what most people who use math end up doing with it, is trying to help us thinking about what makes sense in the world around us and be able to answer problems. Today you're going to see some fairly realistic, but also somewhat contrived word problems. In a more realistic setting, you have data and you analyze it. We're going to look at three situations today, and we're going to try to develop an appropriate model, and we're going to find what that entails. So here's our first situation. There is a business that wants to find the price to sell their product that will earn them the most revenue. Revenue is how much money they make. It's how much money they make. They run a study that finds revenues, which is how much they make, at various prices. A table describes this model below. So here's this table. When they sold their product for $2, they made $16. When they sold their product for $3, they made $21. When they sold their product for $4, they made $24. When they sold it for $5, it made $25, and it made $24. When I first look at this data, the first thing that I notice, and what I always want to do when I am trying to make a model, is to decide what type of function best models the situation. And in this case, there's a function that matches it exactly, although in other cases, you might have to use an approximate model. The first thing I notice is that the more they charge, the more money they make, but then at some point it starts going back down. And I might like to think about why this would or wouldn't make sense. Well, if you charge too little money for something, you're just not going to make very much. But if you charge too much, you might not make as much money because fewer people will buy it. And this is actually like the model we're going to use here is a very real world economic model. And so we're going to start by analyzing it. And when I see something that goes up and comes back down, I think of two possible functions. I think of a quadratic function, and I think of an absolute value function. Both of these could be the model for this situation, and so I want to figure out what's going on. And the way from a table to tell is, of course, to find what the difference is. If it's an absolute value function, what I'll be looking for is two different constant differences, one increasing and then one decreasing. If it's a quadratic function, I'll look for a constant second difference. So I noticed that the revenue went up by 5 here, up by 3 here, up by 1 here, and then down by 1. It does not look like an absolute value function because there was no constant rate of change. So I'm going to look and see if there was a constant second difference. So -2, -2, -2. There is a constant second difference, which means a difference in the differences. And so this tells me it's quadratic. I definitely want to use a quadratic because there is a constant second difference. Okay, and this should make sense. Okay, so like the more I charge, I'll make more money for a little while, and then if I start charging too much, if you're trying to sell a calculator and you're charging like $1 for it, you're not going to be making enough money because even if you sell a whole bunch, you're going to lose money on what you have to pay for the calculators. But if you're trying to sell a calculator for $500,000, nobody's going to buy it. Okay. So now let's look at what price should they choose. Well, we can do this without really any math. We can just look right here and see that it went up and it came back down. This is the vertex point. They should choose to sell for $5 per unit, and they'll end up making $25. And next question is, what is an appropriate domain and range for this model where for different prices they will make different amounts of money? Now this is the hard part. So this is like the hardest part, is to figure out like what are the possible things this model can make sense in. And so I know that it doesn't make any sense to charge less than $0, right? Like you're not going to charge negative. And so there's kind of this base lowest number, and this is for P. The lowest P that makes any sense is 0. because you're not going to charge less than $0. Now the question is there a highest price that this model makes sense for? And so what I might need to do is find where this starts coming back down, and I'm going to keep going. So 7, it will go down by 3, and so I know it'll be 21. I can also just use the fact that it's symmetric. 25 is here, 24 is here, 21 is here. 8 would be 16. That's down by 5. I know this will go down by 7 because there's this constant second difference where the second difference goes down by 2 each time. So down by 7 would be 9. And then down by 9 next would get me to 0. And so if I sell for $10, I'll make no money. And so it doesn't really make any sense for this model to go higher than this, because if I sell for $11, I won't make negative $11. I just won't sell anything. And so the lowest price I could sell for is $0. The highest price is $10. That's the highest thing that makes sense. So I'm not selling it for negative. I can't sell for over 10 and then make negative money. That's where the model stops making any sense. And so my domain is going to go from 0 to 10. The next thing to think about is this discrete or continuous? And discrete means, could I sell in between prices? Like, okay, I know I could sell 2, 3, 4, 5, 6. Could I sell something for $5.50 or $6.17? And the answer is yes, those make sense. I could sell for those amounts and I would get revenue somewhere in between here. And so because the in between makes sense, I'm going to say that the domain is going to be continuous. We have a couple ways of doing this. We can say 0 is less than or equal to the price, which is less than or equal to 10. We always say less than, and the price could equal 0, and the price could equal 10, but it's got to be somewhere in between there. We can also use interval notation. We want to be able to write it this way. We use a bracket to show that the price could equal 0, comma, 10, bracket, because the price could equal 10. And so these are both correct ways of writing the domain, and you want to know both of them. The range is what are all the possible revenues? Well, I know the lowest amount of money I can make is 0 money. I can't collect negative dollars, although my profit could be negative. Revenue is just how much money did you bring in, not how much money did you lose based on the prices. This is just the revenue. And so I know the revenue cannot go below 0. So again, the revenue, the low has to be 0. And the high, what is the highest revenue I can make? Well, I can actually see that right here. The highest revenue I can make is 25. Is it possible to make in-between values? This table skipped from 16 to 21. Is it possible to make $17? And the answer is yes. If I charged 2 point something dollars, I would make $17. And this is easiest to see from a graph. There's going to be somewhere, even though the integer values for prices will give me places where it jumps over, I can tell that there will be in-between values where I can make in-between amounts. There is some price I could charge that would lead to me making $21.30. And so I know it's going to be continuous. And so 0 is less than or equal to R, which is less than or equal to 25, or of course 0 to 25. We use brackets here and or equals to because I saw there was a place where I did actually make exactly $25, and there's a place where I could in fact make $0, and so I need the or equals to at the bottom. I can't make lower than 0, I can't make higher than 25, but I got there. All right, so now the last question is, does this make sense? Okay, so I'm going to use a graph to kind of model this, to help us model this. This was our maximum value. When we sold it for $5, we made $25. When we sold it for $4, we made $24, which is just a little bit under 25. When we sold it for $3, it was $21. And same for 7. $8 got us down to 16. $9 got us down to 9, which is just under 10. And $10 got us to 0. And I'm going to use the fact that there's an axis of symmetry here to just take these same points and say I know they'll be on this side. So I'm going to use this to save me some time because we want to do things as fast as we can. And so here's our graph. I need to do a slightly better job with my labels. So I haven't labeled what this is down here. So the X variable is price that I'm selling something for, and that's measured in dollars. And the Y variable here is revenue. That's also being measured in dollars. Okay. And so here we go. So this says, if I sell for no money, I will make no money. Okay, and that should make sense. If I sell for like, the more I sell it for, the more money I will make until I start selling it for too much, then I'll start making less. And if I sell it for too much, I'll stop making any money. And the model ends here because it's not like if you sell it for more money, you're gonna make negative amounts. This is where the quadratic function ends. You can't sell for negative amounts. And so these parts of the graph aren't there. This function needs a domain restriction. For those of you who are interested, this function is y equals, let's see, this would be 10x minus x squared. Or I guess I should write it as a function of p. So r of p, the revenue based on the price, is 10 times the price minus the price squared. But you don't need to know about this yet. This is just an extra piece of information. Okay, let's look at our second model, our second situation we want to model. So here's a train that is traveling on a straight track at a constant speed of 50 miles per hour. I'm going to go underline constant speed because that seems important. Towards and then through a train station without stopping. Okay, so I'm going to start. Sometimes when I'm modeling, I find it helpful to like get a visual of what's happening. There's some sort of train. Okay, I don't know. I'm not good at drawing trains. That's my train. Toot toot. Okay, so here's my train, and it's traveling at a constant speed of 50 miles per hour. And it's traveling along a straight track, and it says it's traveling towards a train station. I don't know what a train station looks like, maybe like this. And then it goes through it without stopping. It keeps going. Okay, and I want to know how far away from the train station the train is at various times. It tells me it starts 200 miles away, okay? So I know that this distance is 200 miles. I can add to that. And I want to know how far away is this train at various times. So I always want to think about like, what does this feel like? What does it look like? Well, the distance the train is away is 200 miles. And since the train is moving towards it, the distance away is getting smaller, okay? But at some point, the train goes to the other side and the distance away from that train station starts getting larger again. So I can kind of feel like, okay, so it's getting smaller then larger again. So again, maybe it's quadratic, or maybe it's some sort of absolute value where the distance is getting smaller and then larger again. And I've made a table here. I've labeled how many hours the train has been traveling and the distance away from the train station in miles. I've also made a graph here, distance away from the train station in miles and the time spent traveling. So let's think. Is there a lowest value for how many hours the train could be traveling? And yes, the lowest answer for our model is probably going to be 0. So when the train is 0 miles away, 0 hours, when the train has been traveling for 0 hours, it is 200 miles away from the train station. So we knew that already. Okay, the question is, the lowest distance it will reach is it will be 0 miles away from the train station. When will that happen? Well, it's traveling 50 miles per hour. So it goes 50, 100, 150, 200. It will take 4 hours for the train to reach the train station. And what's happening in between there is each hour, the train is getting closer to the train station. So that distance, I'm going to have, I want it to start at 200. The y-intercept is going to be 0, 200. So what should I count by? Let's count by 50s. This is something we want to do when we're making a graph, is decide what to count by. And since I know I need to get up to 200, I'm going to count by 50s, 50, 100, 150, 200. I could have been a little bit more neat when I was making this graph. And so after 1 hour, the train is 150 miles because it's going 50 miles an hour towards the train station. So now it's only 150 miles. After 2 hours, the train is 100 miles away. After 3 hours, the train is 50 miles away. After 4 hours, the train is 0 miles away. And after 5 hours, well, the train was at the train station and now it's gone another hour away. And so it's 50 miles away from the train station. This is distance away from the train station. So it got closer, and I'm gonna go ahead and connect these. Closer, and then further away. And I'm gonna put an arrow here, but I am not gonna put an arrow here because the train's not going back in time. So the question is, what can we use this model for? Well, you know, I don't know if you're familiar with it, but trains often share tracks. And so sometimes they have to switch which track is actually being used. And so maybe you want, when the train is less than 10 miles away, you want this track to switch over from one train track to another. And so anytime the train is somewhat close, you know, like in this area, you want to be able to switch the train tracks. I don't know. There could be a lot of different reasons we could use this model. Maybe their Wi-Fi signal is only going to work when they're a certain amount away and they need to know where to build new Wi-Fi towers or something like that. I don't know. But we want to know how far away the train is at different times. We also want to be able to say a domain and a range. So the domain is what are the possible times that makes sense. And we always want to start out, is there a lowest time that makes sense? Well, they told you the train started traveling, right? And it started 200 miles away. We don't know if this model applies before then. Maybe the train was stopped or hadn't gotten up to 50 miles per hour yet when this stops. And so we can't really go backwards in time. And so the lowest value is going to be 0 hours. So 0 hours is the lowest because we don't know what happened before then. And the question is there a highest time? And if we don't know a highest time, like maybe it could go 6 hours, 7 hours, 8 hours, 9 hours, 100 hours. I don't know. A lot of times we'll say the highest just infinity. And we might come back to this later if we want to be like, if I had a boss who asked me to make this model and they say, okay, well, like, can we put an upper limit on it? Maybe I would look at like, how much coal can a train carry and go before it needs to stop? And based on how far it can go before it needs to stop, I would make that the highest number. But if I'm not sure, I can just put in infinity as a placeholder. So the domain is going to be all the numbers between 0 and infinity in this case, because we don't know when the train would have to stop. There's not really a clear answer, although we could go get that information later if we want to build a more robust model. The other question with the domain is it discrete or continuous? Again, it's about whether the in-between values make sense. Could you find out where the train is at 0.5 hours? And the answer is yeah. At half an hour in, it would be 175 miles. We can almost make this part of the graph is actually a linear. We'll get to piecewise functions later. This can be thought of as two linear functions. So this part we could write as like y equals negative 50x, that's the constant rate of change, plus 200. Now, this is only going to work for the first 4 hours. So this is when the time is between 0 and 4. This has a domain restriction to it. But you can see because it's linear that I can find exactly when the in-between times will be, and they make sense here. Yeah, the train can be 175 miles away at half an hour, or 0.3 hours, or 2.6 hours. All of those in-between times make sense, and so we're going to use a continuous domain. So the lowest value is 0, and so the domain is going to be, I'm going to use interval notation here, could be 0, up until infinity. And remember, when we use infinity, we always use a parentheses because it will never get to infinity. So this says the possible times for this model go between 0 and infinity. And this infinity is mostly just saying like we don't know when it would end. Okay. Of course, another way to write this is 0 is less than or equal to t, which is less than infinity. Or if it just goes one way, we could just say t is greater than 0. So the time is greater than 0. All three of these ways are ways to write the domain. Okay. The range. The range of this function, it's really easy to tell from the graph. Is there a lowest distance that this train will be away from the train station? And the answer is, yeah, the lowest distance is 0. I can see that the distance was 0 right here. It's never going to be a negative distance away. And so I know my low value is 0, and it gets a bracket because it actually reaches 0. And is there a highest distance away? Well, it started at 200. I know it's going to get at least to 200, but I'm not sure when the train is going to stop. This part keeps going up, and so the distances keep going up and up and up depending on how long it goes. And so this domain is also, or this range is also 0 to infinity. And so another way to write it is that the distance goes between 0 and infinity, or just that the distance is greater than or equal to 0. Hopefully you had a question about this earlier. This should have said the time was greater than or equal to 0, rather than just greater than. The time could equal 0. This model made sense for that. Okay? So that's our second situation. It's an absolute value model, obviously, and it looked like this constant speed. You might have thought linear, but what's happening is the distance is going down and then back up because we're not measuring how far the train went. It's how far the train was away from the station. And so the distance went down and then back up, which made two different constant rates of changes. Even though the train never changed speeds, the distance away changed directions. All right, our last example is going to be in a biology lab. A petri dish initially contains 10 protists. Protists are, just a little bit bigger than bacteria. We should know from biology, I hope. They double. The number of protists doubles each hour. And after 13 hours, the scientist observes that the petri dish is full. Petri dishes are these little round things that we grow stuff in. There's usually an auger at the bottom that the whatever is growing there can eat. And so we want to model this. All right, so we don't have a table or a graph, and so we want to think about what's going on here. The key thing that I see here is that they double each hour, and doubling means multiplying by 2. This should be a clear indication that if there is a constant multiplier, we know we're going to need to use an exponential model. There's an exponential model. There's going to be a constant multiplier. And I'm going to go ahead and make a table. So the two variables here are the number of protists. So the number of protists is going to depend on how much time goes by in hours. So for different times, I want to see how many protists there are. And this is going to be in hours. The time is measured in hours. And I know when no time has passed, when it first starts, initially means time equals 0, no time has passed. Initially means at the beginning when no time has passed. There were 10 protists. And it said it doubled each hour. So that means every time an hour passes by, we're going to multiply by 2. And I could keep doing this, 160, whatever. The numbers are getting kind of big here. Tables don't need to show all the different values. They just need to show some of them. Okay. And let's look at what a graph of this would look like. Okay, so I guess I'm going to count by 10s here. 10, 20, 30, 40. And at 0, there were 10 protists. This is time in hours. This is protists. I always want to have a good labeling of what is going on in my graph. After 1 hour, there were 20 protists. After 2 hours, there were 40 protists. After 3 hours, it's going to be way up at 80. That's going to be off the graph. And so I end up with this graph that looks like this. Now, maybe I shouldn't have connected it. I do need to think about whether this is discrete or continuous. So let's think about the time first. Is there a lowest amount of time? So I'm going to come up with the domain. And so I want to think, what is the lowest amount of time I could have? And obviously that's 0. There's no negative time before we started. Is there a highest amount of time for this model? And the answer is yes. After 13 hours, the petri dish is full. And that tells us that, when the petri dish is full, they're probably not going to keep doubling. This model will fall apart, and they won't keep doubling. Maybe they'll stay constant. Maybe they'll die. We're not exactly sure what's going on, but it won't keep doubling because it's already full. So I'm going to say the highest is 13 hours. Now, the question is, do all the times in between make sense? Like, could I find out how many protists there are after 2.5 hours? And the answer is yes. And so my times are going to go between 0 and 13, and they could equal 0 and they could equal 13. Of course, I could write this like this, 0, 13 in interval notation. This means all the times between 0 and 13 make sense. And my range is going to be about the number of protists. And so I want to think about the lowest number of protists. And the lowest number of protists was 10. So it doesn't get down to 0. There were never 0 protists. What is the highest amount of protists there ever are? And the highest amount of protists, we didn't really get there, but it's going to stop after 13 hours. And so I can use a calculator and do 10 times 2 times 2 times 2 times 2. So 10 times 2 times 2 times 2 times 2. This is going to happen 13 times. We can use ... here to show that it'll happen 13 times. And there's a shortcut way of writing this. This is 10 times 2 to the 13th power. And just to show you that these are both the same, 10 times 2 to the 13th power is the same as 10 times 2 times 2 times 2, and I typed this out 13 times. It was kind of annoying. And we get that at 13 hours, there are 81,920 protists, and that is the high. Now the question is, do all the in-between values make sense? Well, yeah, I mean, we could have like 15 protists, and just because in the table we skipped over 15 protists doesn't mean that there would never be 15 protists. There probably were at some point. But do all of the in-between values make sense? Are there ever going to be, we always want to think of like decimal numbers. Are there ever going to be 13.5 protists? And the answer is no. You either have a protist or you don't. It's a discrete amount, which means only individual numbers of them make sense. And so this is discrete. And so we cannot say all the numbers between 10 and, we couldn't say this. Because 81,920. This wouldn't make any sense because this would be saying that P could equal like 17.6 protists. And this is not correct. You won't ever have a decimal number of protists. And so even though the domain was continuous, the range, we're going to need a discrete domain. And we, of course, use braces to write that out. And when we're using a discrete domain, we start with the lowest number. We put a comma, we put the next number. And sometimes I'll see kids put 10, 20, because that's the next number we had in the table. But that's not right. The next lowest number of protists we could have is 11. You can have 11 protists, and 12, and 13. And we do not want to spend all day getting up to 81920. So we're not going to write them off. Instead, we're going to put ... which means this pattern keeps going, 10, 11, 12, 13, 14, 15, 16. But it's going to end, and so we put a comma at the end and say 81,920. And so these are the different possible numbers of protists we could have. So I hope we can see how our main idea here when we are modeling is we want to be able to figure out what type of function and we can do that by using the ways we've been identifying functions. Does it have a constant rate of change, or a constant multiplier, or a constant second difference, etc. So we want to figure out what type of function it is, and sometimes just the shape of it. Like, oh, I noticed it went up and back down. Well, it's either going to be a quadratic or an absolute value, right? So what type of function? We want to be able to make a table and graph. We want to be able to answer some questions, like what makes sense? What's the highest number of protists there's going to be? What is the maximum amount of money we can make? And we want to think about what makes sense, because truthfully, we use models to communicate with other people, and we don't want to look like idiots when we say like, oh, yes, when you charged $15, you made negative $400. Like that isn't a thing. And so you need to know where the model will end to be able to say, look, okay, these protists are going to double for 13 hours, but then after that, this model is done and it stops. The same is going on right now. I just want to make a quick thing about COVID. We were actually really interested in modeling it as an exponential, but at some point it stops being exponential. And if we aren't doing any social distancing or anything to stop the spread, it starts out exponential, but then at some point it actually stops being exponential and starts looking like this. And this is a different kind of model, but the beginning part is very much exponential. It has a constant multiplier. That's how viruses naturally grow. And I'm going to stop on that. This is something that's a very real world thing that we need to decide how to model things so we can figure out what are the best decisions we can make, either as a business or as a society, in a government, to make sure we're doing things adequately and we're analyzing them correctly. So